Descent. To descend from hover where total rotor thrust equals the all-up mass, the collective lever is lowered. Total rotor thrust decreases and the helicopter enters a descent. As the rate of descent increases, there is, by virtue of downward motion, a relative airflow up through the rotor. This reduces the induced airflow and inflow angle, and the angle of attack increases. Total rotor thrust increases. With the increase in total rotor thrust, the descent is stabilized. The rate of descent depends on the difference between the power available and power required. If there is power available at zero forward speed, then the descent will be vertical. Minimum angle of descent. To decrease the angle of descent to give maximum range over the ground, the helicopter is flown at the greatest total rotor thrust, which gives the least rotor drag. This is the tangent to the power required curve, VMD. Descending at any other speed will increase the angle of descent. Minimum rate of descent. For any descent where power available is less than power required, the minimum rate of descent will be where the power required is at minimum. Effect of wind, mass and configuration. Wind. Wind will affect flight path glide angle and range over the ground. A headwind increases the flight path glide angle and decreases the range. A tailwind decreases the flight path glide angle and increases the range. Mass. Provided the helicopter is flown at the VMD, for the mass under consideration the angle of descent will remain the same, but the rate of descent will increase with increasing all-up mass due to the increase in true airspeed at the higher VMD. Rate of descent equals gradient multiplied by true airspeed. Configuration. Descending with gear extended or with external stores will increase the drag. Descent angle will increase.